Greetings. I want to open with an apology that my schedule did not allow me to make the trip this weekend. I had planned on being there. When Jim and I originally discussed this session, the purpose of it was based on the fact that neither he nor I were able to travel to Catania for the celebration there of Alan's career. I think it was last September, and that we should have a session in the United States because I think a lot of you in the room right now were in the same boat with us. You weren't able to travel to Catania that early in the semester, so we thought it was really fitting to have a celebration for Alan here. And I insisted that I give the first talk because I think, even though I can't see who's in the room right now, I've known Alan longer than anyone there. I actually met Alan in 1987 when I interviewed at Hope College for a job. And especially the younger people there in the audience, make note of this, that you can go on an interview and it not work out. You either not take the job or not get the job. And a lot of good can still come of it, because this is how I met Alan. I think if I hadn't gone on that interview, I would not have. And it began a very long relationship, which involved a little bit of collaboration, but more admiration on my end of his accomplishments. And I'll get to talk about a couple of them today. A true view of Alan's career should really take several hours. So I have 20 minutes. So what I've done is I picked two results in Alan's work that I really admire and I think are really high points in what he's done mathematically. And I share those with you and talk a little bit about them and talk a little bit about Alan's career. So if I can share the screen here for a second. And again, if this didn't work, Jim was going to give this talk, so I put his name on there. And let me emphasize the word in the title here, enduring, because as we get towards the end of the talk, I'll kind of try to emphasize to you why I think Alan's mathematics is going to be enduring, and it's going to continue, as I'll get into some detail about. So there's Alan. He did his BS at Virginia Tech, both his MS and his PhD at Wisconsin-Madison. His dissertation was titled "On Rings Without a Certain Divisibility Property." He wrote this under Hiroshi Gunji. And Gunji, if you look at his record, is mainly a number theorist. So I believe he teamed up with Donald McQuillan, who was there at Wisconsin at the time, and started working on some things that were a little more algebraic than number theoretic. But if you look at Gunji and McQuillan's early papers, they're really number theory papers. But they got interested in polynomial rings. And in particular, they got interested in not Alan's dissertation title, but the opposite. They got interested in rings with a certain divisibility property. And Alan's dissertation dealt with the opposite of that. But I'm going to talk a little bit about why I think that's so important when you view Alan's career and his major accomplishments. So here's Alan's career with respect to where he's been past his PhD degree. I talked a little bit about Hope College. I've heard Alan many times joke that you could make a all-star team out of the mathematicians that have left Hope. I think Alan might be the captain of that team. After he left Hope, he spent a couple years at Lawrence and then began a long, around 32-year career at Ohio State Newark, which gave him privileges there on the main campus, which was, we'll see in a second, he certainly took advantage of. He also spent a year visiting at North Carolina, Charlotte with Evan Houston and Tom Lucas, and that led to some collaboration between he and Tom. He had, and I guess this is it. I don't know if there's any more one else left in the pipeline. 7 doctoral students. I think many of these people are in the audience. Greg Oman, Nick Werner, Michael Stewart, Daniel McGregor, Austin Antoneau, Nicholas Bruno, and Beyond Liu. I've corresponded with Liu a lot. He's gotten interested in integer valued polynomials and some things that I've been interested in. But Alan certainly, toward the latter part of his career, did his more than his share of mentorship and getting people ready to listen to talks like this. Now, if we look at Alan's career in totality, on Google Scholar right now, he has 54 papers. They've been cited well over 1,000 times. One thing I want to point out about Alan, and until I started to get ready for this talk, I didn't know this, but he, of these 54 papers, 23 of them have appeared or will appear over the last 12 years. So not quite half, and well more than a third of his career has occurred in the latter quarter of his career. I think that's really impressive. You know, that is against the grain of common wisdom that most mathematicians do their best work early in their career. I think this Alan's certainly a counterexample to this. During his career, he's had the opportunity to work with some of the leading people in our field, certainly the leading people in integer valued polynomials, Cahen and Chabert. He's had a really productive collaboration with Marco Fontana that we'll talk about in a second, Bill Smith, Bill Heinzer, Bruce Olberding, my good friend Kang, Francesca Tartarone, Tom Lucas, who I mentioned before, Lee Klingler, Moshe Reutman. We're going to talk about a paper that Alan wrote with Moshe here in a few minutes, and Dario Spirito in Catania. So here are Alan's top 5 cited papers, according to Google Scholar. And a couple of comments about this. The first is both the papers I'm going to talk about aren't on this list, which I was really amazed when I started to do this. Notice that the top 3 were papers that he wrote with Marco, and 2 of those are essentially expository papers. I think there's new results in them, but they're in conference proceedings, the second and the third bullet points there. But if you spend any time looking at papers, and as an editor, I actually do this a lot, and you look at numbers of citations, a paper cited more than 30 or 40 times is a really, really powerful paper. It's had a lot of impact on other people. And look at this, these papers with Marco, these 3 papers, well more than 250 citations on those 3 papers. And notice none of those are about integer valued polynomials. The first 3 are about Kronecker function rings. So again, I think that demonstrates Alan's breadth as a mathematician. He just didn't focus on one thing. I've heard this as a criticism of some people in integer valued polynomials, and that's all that they do. Certainly, Alan does not fall into that mold. Also notice all 5 of those papers have an Italian co-author. There's probably a joke there that can be told, but I couldn't think of it. Here's Alan's first paper. I mentioned his dissertation title on rings without a certain divisibility property. It's in the Journal of Number Theory. Again, I think that's significant in the sense that, you know, his early part of his career was guided by number theorists. So here's his first paper out of the Journal of Number Theory. And let's look at the definition of what it means for a ring to have this divisibility property, which Gunji and McQuillan called a D ring. So let R be a ring with field of fractions F. We call R a D ring if whenever F and G are non-zero polynomials in R bracket X, with the property that F of A divides G of A for all but finitely many A, then F of X divides G of X in F bracket X over the polynomial ring over the field of fractions. Now, Alan's first 3 papers dealt with non-D rings. But if you look at this definition and you look at those papers, it's not a surprise the direction that his research went into. And I think this was heavily influenced. He visited with Donald McQuillan. I don't exactly know what year it was. It was sometime in the mid 80s because I went a couple years after that. He started to think about integer valued polynomials. And again, I think most of us in this room know what an integer valued polynomial is, but here is the definition. If D is an integral domain with quotient field K, I'm looking at the subset of polynomials over the polynomial ring over the quotient field that map big D back into itself. Okay. So again, a notion that for most of us is well known, and a lot of us have worked at times with integer valued polynomials. Now, from 1995 onward, over half of Alan's papers specifically deal with integer valued polynomials, and a lot of the other ones deal with them in some way, shape, or form. But, you know, when I look at integer valued polynomials, I did a lot of work early in my career with integer valued polynomials, having worked with Bill Smith, who was a big integer valued polynomial guy. What was really interesting about it, there was a huge open conjecture when I first started looking at this about integer valued polynomials. So in the base case here, where the integral domain D is Z, int D is a proofer domain. This is an old result of Brazolus. And therefore, the study of the relationship between the proofer property and integer valued polynomials became really popular in the 1980s and the 1990s. You'll notice this paper of Brazolus was 1979, and yes, it's in Communications and Algebra. From that point, for almost 20 years, the leading people in this area, Gilmer, Cahen, Chabert, and McQuillan, all worked on various forms of this base problem, for which integral domains D is int D a proofer domain. And I know that Gilmer and Chabert and Cahen worked tirelessly on this. And there's several papers that you can read that they wrote leading up to this result that we'll talk about here in a second that Alan came up with. Let's look at the history of this for just a minute. Somewhat simultaneously, Chabert and McQuillan showed that if D is Noetherian, then int D is proofer if and only if D is a Dedekind domain with finite residue fields. This was in the mid to late 80s. Also in the late 80s, Chabert showed that if int D is proofer, then D is an almost Dedekind domain with all residue fields finite. 6 years later, Chabert provided a double boundedness condition, which is necessary for int D to be proofer, but it was not sufficient. And a few years later, Alan wrote a paper on sequence domains that proved a version of this double boundedness condition, which is necessary and sufficient for the problem for the class of almost Dedekind domains satisfying this condition, which he termed sequence domains. Now, to look at Alan's result, let me set the stage a little bit. Let's let D be a non-Noetherian almost Dedekind domain with all residue fields finite. For a maximal ideal big P of D, let V sub P upper N represent the normalized valuation on K associated with the maximal ideal P. I'm going to assume that the characteristic of K is 0. Alan, in the proof that we're about to look at, adjusts that to arbitrary characteristic toward the end of the proof. So the characteristic 0 case is really the big one. And there's two sets here of interest, big F sub P and big E sub P. And so big F sub P is the set of cardinalities of the residue fields of the prime ideals P for D mod P that little p appears in. And E sub P is the image under this normalized evaluation of P for all the prime ideals big P that little p lays in. And Alan's definition is that we're going to say that D is doubly bounded, provided that E sub P and F sub P are bounded sets for each prime little p which is a non-unit in D. So for every prime. So this is a very strong condition, this double boundedness condition. And here's the paper. Using this double boundedness condition, Alan was able to solve the problem. It's in the Proceedings of the American Math Society, 1998. So people worked on this for not quite 20 years, almost. And the theorem is very, very simple. And notice the paper's only 4 pages long. So once you determine this is the condition that you need, arguing it is not horribly involved. But again, int D is a proof or domain if and only if D is doubly bounded. And as I said, a lot of people worked on this for a lot of years. And so kudos to Alan. He solved the int D when int D is proof or problem. Now, a lot of people might think that that's a good hat to have hang your career on, solving a problem that was open for such a long time and worked on by so many people. But that wasn't the only time Alan was involved in doing such a thing. A few years later, in some joint work with Moshe Reutemann, he solved another very long open problem in a little different direction. Let's talk about contents of polynomials for a second. So if R is a commutative ring and F is a polynomial in the polynomial ring over R, then the content of F is the ideal of R generated by the coefficient of F. Okay. The Dedekind-Mertens lemma, very well known, states that if F and G are polynomials in R bracket X, where the degree of F is little m and the degree of G is n, then the content of F to the nth power times the content of F times the content of G is the content of F to the nth power times the content of Fg. And so the polynomial is said to be Gaussian if you can cancel up there. If the content of Fg is the content of F times the content of G for every G. Fix F, that's got to work for every G. Notice that we always have that the content of Fg is contained in the content of F times the content of G. So in the Gaussian case, we actually get equality. And Gaussian polynomials are well studied for 50 years or more. It's well known that if the content of F is invertible, then F is Gaussian. Now, it took me a little bit of work to put my finger on exactly the genesis of this problem, because you can find several references to the fact that Kaplansky conjectured the converse of this without proof. You can't find it in one of Kaplansky's papers. There's a set of notes that Vasconcelos put together that Sarah Gloss cited several times that indicates this. He obviously discussed this problem with one of his PhD students, Sang. It's mentioned in his thesis in 1965. And this conjecture, timing it from Fang's thesis, was open for over 40 years. And Moshe and Alan solved this. The content of a Gaussian polynomial is invertible. This is another paper in the Proceedings, December 2004. This one's 4 pages long. So again, once you put your finger on what you need, the argument flows in a really beautiful manner. Now, what do you need? You need a couple of facts that I'll review here real quickly. The Gaussian property of a polynomial is local. That is, F is Gaussian if and only if the image of F in the localization of R at M bracket X is Gaussian for each maximal ideal M of R. Because of that, to prove the conjecture, they were able to assume that R is quasi-local. And moreover, it allows one to generalize the conjecture to the effect that if R is locally an integral domain, that is R mod M, or excuse me, R localized at M is a domain for each maximal ideal big M, then a non-zero polynomial R bracket X is Gaussian if and only if its content is locally principal. And keeping these three things in mind, Moshe and Alan solved the conjecture with the following theorem. Let R be a ring which is locally a domain, then a non-zero polynomial over R is Gaussian if and only if its content in R is locally principal. Now, one thing about looking at that paper again that I really appreciated was the end of it, which is not that theorem, but this proposition, which I think indicates how hard a problem this was, why it was probably open for 40 years. A factor of a non-zero Gaussian polynomial of an integral domain might not be Gaussian. In fact, if R is an integral domain and F squared is Gaussian, it may not be the case that F is Gaussian. So this Gaussian property, and if you Google this, or you go into Google Scholar or whatever you use and look up papers about Gaussian polynomials, there's a lot of them. This is probably why. It's a really, really complicated property. Now, I've gone about a minute over, so let me wrap this up. And normally at the end of a talk like this, you congratulate someone on having had a great career. I think I've already done that, but I want to emphasize that I don't think in any way, shape, or form Alan's career is done. I think we're going to see a lot more amazing mathematics from Alan, but congratulations on your retirement. And again, I apologize that I couldn't be there. Let me close this down. I hope you all have a great meeting, and I hope I'll see you again at a meeting like this very, very soon.